I'll just say it's acting irregularly compared to my. I'll live with this. All right.
Sounds good. Give me a second. Let me do one more thing. Invite the people from my group, my research group, in case I want to join, but I think we're. Otherwise, I think we can go ahead and get started. Let's try streaming, Christian. Oh, is it live already?
We're streaming.
Oh my Lord. People have been watching me be all sleepy all this time. All right. So hi everybody. I'll excuse myself for being extra sleepy because I just got out of a red-eye flight to Europe, and so I don't know where my brain is right now. But it's a real pleasure to have Under Work Aloud, my academic older brother. He's a staff scientist at Lawrence Berkeley National Lab. He's an expert in lattice QCD, effective field theories, and a few other things. And he's going to tell us about some of those aspects that he wanted to share with you guys. So, Andre, you're in charge. Take it away. I'll be in the background rocking.
Okay, thank you very much, everybody. Raul, Christian, Andrew. What do I want to say? Well, first of all, this is actually a picture from my work looking over the San Francisco Bay. And so if you don't know, which I assume you don't, where I work, Lawrence Berkeley Lab is sitting on the University of California, Berkeley campus, which is just over the San Francisco Bay, east in the town of Berkeley. And you probably know that San Francisco is famous for having a lot of fog. And so this is a picture of the fog that has been sucked in on some summer day because, you know, just over the hill behind us to the east, it gets pretty warm, heats up the air, and then you can't see it, but the ocean's right out here. And so it sucks all the cold ocean air off the, and then brings in all this fog. And this was a few years ago. Berkeley has this famous little bell tower where they even have a live streaming video because there's some hawks who are raising little young hawks in the bell tower. It's convenient because the bell tower sits right in front of the physics building. And so anytime I want to remember how to find the physics building, I just walk to the bell tower. And all of this is entirely irrelevant for the discussion today, but I just thought I'd tell you this is a typical view that I get looking, well, I don't have a window that sees this, but I have to walk outside, maybe get a coffee and go stare at the bay. Sometimes it looks much nicer. You can actually see San Francisco and the Golden Gate Bridge. But in this particular instance, you see this crane here. They're actually building the new supercomputer at the NERSC, National, I can't remember what NERSC stands for, but there's a big supercomputer sitting here now. And also, let me just say, as we go, please, you know, in the middle of what we're talking about today, if you have any questions at all, please ask them. I will try to pay attention to the questions, like I guess through the chat window, maybe might be the easiest, or the Q&A. So if someone asks a question and I don't see it, also, if somebody else can speak up, that'd be great. All right. So what do I want to talk about? What I want to talk about in some sense is, you could ask the question, how do we actually know what we say we know? You know, when we're interacting with friends and family in life, we often express that we know things with varying degrees of confidence. And if you grew up reading comic books, you and your friends have probably had the argument, you know, who's going to win in a fight, Superman or Batman? Or if you have some other favorite comic book hero, you'll pick some other ones. And you'll say things like, we know absolutely that Superman would totally beat up Batman. And if you watch the movie, I'm sorry, because the latest movies weren't very good. But anyway, maybe you enjoyed them. Maybe I'm just old and don't like these new movies. But what I want to say is, so what does it mean, you know, when we say in scientific field to know something? And really, I guess what we want to do is come up with some way in a quantitative sense to quantify our confidence in a statement being true or false. And so at the very heart of making statements like this, we have to understand statistical data analysis. And that's going to be what I'm talking about today and on Thursday. So today will mostly be, I'll just call it a refresher. And I'm sure for some of you, this might be new material. And for some of you, you might find this well-known and boring. But bear with me, I'll be setting up the language we'll talk about. And then on Thursday, we'll actually get our hands dirty, so to speak, and try to do some actual fits. And maybe depending how brave I am, we might do some fits live. Maybe not, we'll see. Okay, and then also let me just give you a couple references. I can't tell you that these are necessarily particularly very good or very bad references, but these are the references I know and I'm familiar with. And at least they're good enough that I would recommend them as a reasonable place to go read about a lot of the things we're going to discuss. Because certainly I won't have the chance to derive in any detail most of what we'll talk about today. This will all just be in some sense stating things that are known to be true by the community. And if you want to understand why they're true, you have to go do a lot of homework, maybe take a class or two. And we'll be talking about sort of both what's called frequentist analysis, as well as you've probably heard of Bayesian analysis as well. So there's sort of two different philosophies for how to think about interpreting, information about the world based on the data we have, either from a frequentist viewpoint or a Bayesian viewpoint. And also myself, I grew up learning about statistics and data analysis completely from a frequentist viewpoint. And I was initially, I will call it, I had a biased prejudice against the idea of Bayesian analysis. And it wasn't until I finally had someone working with me who was more of an expert in Bayesian analysis, and I really sort of got to get into it, which is, hopefully, when you recognize you have a bias, you might want to overcome it anyway. But in this case, it was when someone was working with me who I could ask a bunch of questions to. I got to learn much more about Bayesian analysis, and I'll come back to this idea, I guess Thursday, probably not so much today, but I've come around to being a sort of, a much bigger proponent of using Bayesian analysis now than frequentist. And the motivation isn't based on the philosophy of these two different ways of thinking about statistics and data analysis. But in my case, a lot of the data I want to analyze, there's a lot of challenges in analyzing the data. So there's a lot of noise. So a lot of times the information we want to learn is only, the easiest way to learn this information would be in a region where the data itself is experiencing a tremendous amount of noise. And so it becomes difficult to very confidently pin down our best estimate of the parameters we're trying to determine. And what I found through experience is that when you implement Bayesian analysis, particularly when you start adding what's called Bayesian constraints to your data analysis that help keep the parameters, they can't wander everywhere, but you say, I have some prior information that lets me say I have a pretty good reasonable belief that the value of this parameter should lie between some, range. And then when you do that, what I've found in practice is you can do, so let me step back one little bit. In general, what we want to do, we're using very valuable, limited computational resources to do the best job we possibly can estimating some parameters. And because the resources we're using are very limited, we want to do the absolute best job we can estimating those parameters. We don't want to give we don't want to quote the value with too big of an uncertainty if we don't have to, because in some sense that wastes this very valuable computing resource. Like if we're just very quote unquote lazy and we just say, well, we know this is a pretty good estimate, and you have a really big uncertainty, then I would argue you've kind of wasted this very valuable resource, because if you want to get ideally what you want to do is get the smallest uncertainty you can without over constraining your answer, like without getting too quote unquote aggressive. And with the Bayesian analysis, what I found is it's much easier to, as a person, to design a way to analyze the data that becomes independent of your personal bias of what you think the answer maybe or maybe shouldn't be, and to start to fiddle with all the possible knobs you can fiddle with when you're trying to analyze the data, and come up with a much more stable answer, such that as you change, say, the number of parameters you use in the fit, that the final answer you get out of what you care about is insensitive to all these possible different choices you could make. And so the other big trick, of course, is you have to make sure when you're doing this Bayesian analysis that the constraints you're putting in to the fit are not predisposing the answer that you care about. They're not influencing that answer. So if you put in a constraint that's too tight, it might influence the answer you get out. And that's a bad situation. And if I try to do the same sort of thing with frequentist analysis, I don't have nearly the ability to control the robustness of my answer. So mostly what we care about is how robust is the answer and how precise can I make it while still being confident I haven't underestimated the uncertainty. All right, that's a lot of words. Let me try to get into what we're talking about today. So, scientifically, when we state we know something is true, it's almost always we state it with some confidence. So this is a word that we'll use a lot, some confidence level. And in this, context, when we say confidence, this has a very precise meaning. And you'll probably recognize that, as you're studying science, here I'm mostly familiar with physics, there's many words we use both in our daily lives. Also, I'll refer to that as colloquially, like when we're talking with our friends or family who are maybe not trained in the same science field that we are, or not trained in science at all. And when we use that exact same word in a scientific setting, they can actually have rather distinct meanings. And so this can often lead to fun discussions with your friends and family, because you think you mean something and you realize, oh, right, that doesn't quite mean the same thing. So for example, the words force and acceleration, these are words that we use all the time in regular life that have a very precise meaning in physics, and sometimes those two don't match up. And so also, you'll notice when scientists are answering questions publicly, maybe they're on TV talking to someone in politics or on the news, and scientists are always very reluctant to say, this is what's going to happen. It's always, well, we're fairly confident this is going to happen. And that's because as you study science more and more, everything we know, we only have some probability of saying this is true. And so we're always very cautious to say this is absolutely true or not true. And so that can sometimes look frustrating when you hear scientists answer questions in what seems like a vague way, but that's because we're trying to be very precise, and this word confident has this precise meaning in science. All right. So getting into all this, of course, what we need to do is we need to understand probability and statistics, because as I said, every time we answer a question, it's like we have some measure of probability that the answer I'm giving you is true. And this is also rooted in our understanding of statistics. And another thing I'll say is these are two topics I found to be incredibly boring when I was a student, both undergraduate and graduate. And I didn't do a very good job paying attention to these classes and studying the subject material. And it was only later after I got more into research, and then it turned out, oh, my research has a very strong stochastic component to it, and what that means is every piece of numerical data we get has some uncertainty on it, and then suddenly these topics became much more important to me. And as with many things in life, as you go through life, you look back and you say, I really wish I'd pay more attention to that. And in this case, I really wish I'd pay much more attention to the subjects of probability and statistics, because then, to have a better foundation for the work I do in my daily life. Uh, and of course, for most of us, it's not true for some of us, but for most of us, the easiest way to learn a subject is when someone else has done the work to organize how to present the material. Like what's the order in which you want to present the material, and what depth of detail do you want to get into? And if you have to figure this out on your own, for most of us, this is more challenging. And so right here I am playing catch up because my foundation in probability and statistics is not as strong as I wish it was. And so now I'm having to play catch up. And maybe you can avoid my fate by going off and learning more about these subjects yourself. Okay. Now here's another interesting way to look at things. In particular, as we learn theoretical physics, and that could just mean you're just learning the subject of physics from an undergraduate or high school level as you go up. The way we learn about physics is we're taught these laws of nature. And we start off with some law of nature, which we can take some initial condition or a cause, and then we can use that law to predict an effect. And so in classical physics, if you know the initial condition exactly, and you have the laws of nature, basically Newton's laws, you can exactly predict the outcome at later time. And then, in quantum mechanics or quantum physics, then we lose this exact predictability, but then what we get is we have some cause has some probability of having different answers. And this is also interesting because we never know the initial condition exactly. We always know the initial condition with some uncertainty or some probability distribution. And then if you imagine there's some uncertainty on the initial condition, even if there's a classical system, that means you can only start to predict the outcome also with some probabilistic determination. And so this notion of having one initial condition having a distribution of outcomes is inherent in quantum mechanics. Like there's no getting around this. Even if you know things perfectly, as we know, we can't perfectly know, for example, the position and momentum of a particle. The uncertainty principle prevents that. But even in classical physics, we cannot know things exactly perfectly because there's always some measurement uncertainty. And so then we're left with this probabilistic outcome. But also the other idea I would like to get in your head is this is not how we actually learn how the world works, right? This is after we've learned how the world works, we can teach the laws of nature, which have this deterministic outcome. And here I'm using the word determinism even in quantum physics, because what I mean in this sense by determinism is not that I know exactly which state I'm going to end up in, but I'm able to run the equations that describe how the system evolves forwards and backwards in time. And so that's this notion of what's called unitarity, which you heard about. Actually, it's related to the scattering theory that Andrew was talking about last week. So if you know how to run the equation, so we know the laws of nature are almost perfectly symmetric going forward and backwards in time. And this is what I mean in this sense by determinism. But again, this is not how we actually learn how the world works. This is, again, after we've learned how the world works, we know the laws, we can evolve the system forward in time. In reality, what happens is we think we know what's going on. We have some hypothesis for what's going on. And then what we do is we observe various outcomes. And then our task is to attempt to infer, based on the observed outcomes, what was the initial condition, or it could be the initial condition, or it could be which is the correct theory that tells me how to go from the initial condition to the observed outcomes. So this is, interesting. It's subtle, but it's an interesting conceptual point to get across. What we really have is a set of observations which have some uncertainty, and our goal is to try to learn what is the underlying cause of getting from A to B. All right. So let's start by defining some quantities. So here we have some, I'm calling it a basic refresher of basic probability. So here we'll note this symbol P for probability. And so this means the probability of A, where A is something, the probability that it's going to be sunny today. Probably depends where you live. And then another important concept is closure. So if you know all the possible things that could happen, AI, here I is denoting the possible different things that could happen. It's a sunny day or it's a cloudy day. And you know the probability of those things, which we don't know for sunny and cloudy days because weather is a very complicated system. Even though it's determined classically, it's so complex we can't know the initial conditions exactly. But if you know the probability of various outcomes and you sum over all the possible outcomes and their probabilities, you have to get one. So this is just stating the saying the sum of all probabilities equal one is really just saying something has to happen. We don't know what it is going to be, but we know that something's going to happen. And if you think you understand a system and you sum all the probabilities and you don't get one, it means you're missing some information, or you've incorrectly identified the probability of different cases so that you're not summing things up to one. And then another important concept that's really happens much more to us in sciences is given my some state B, what is the probability of A? And this is really where the Bayes theorem starts coming in, is like maybe, your starting condition is based on some prior information. This word prior comes up a lot in Bayesian analysis or Bayesian statistics. But again, starting with the state B, what is the probability of A? And this is called a conditional probability. All right. So slightly, just doing a little math gymnastics here. Here, A is the intersection. This symbol A is the intersection. So if you have some overlap of the state A and B, you can predict the probability of A if you know the starting probability of B and how much A and B intersect or how much they overlap. I didn't have a picture for this, sorry. I was thinking about making a picture and then I forgot. But what's interesting is, here's an equation, and you can also then ask, of course, what is the probability of B given A? And this is also given by the intersection of B and A. But then the intersection of B and A, of course, is equal to the intersection of A and B by definition. And so what you get is here the probability of A given B is the probability of B given A weighted by the probability of A and the probability of B. And this is Bayes' theorem. So this is a very simple equation. It doesn't sound very deep, but this leads to a whole line of thinking of how to interpret the world, Bayes analysis. And now
Andre,
let me, yeah.
if you want, you can also connect your iPad and draw pictures if at some point. But just a thought.
Thank you. Yeah, I have it right next to me.
Yeah, it can be a little bit of a pain with this interface, but you're welcome to do that if you want, maybe later.
Yes, there might be two of me. Okay. Okay. I will probably take you up on that. Because then I could probably, if I transfer these slides to my iPad, I could scribble on them too, which might have been even better. So you guys also, I haven't really taught in 7 years, so you're getting, you're my guinea pigs as I start attempting to do a little instructing again. I mean, I've done instructing like mentoring students and postdocs, but that's very different than trying to describe things to an audience. So thank you for bearing with me. All right, jumping back into it. Suppose you have a set of different, and now I'm almost tempted to start drawing immediately. So if you had some set of different possibilities A, and they all have some overlap with B, you can subdivide the probability of B into what you can show is it's the sum of all the probabilities of B given a certain AI times the probability of that AI. Okay, this is, as I'm saying it out loud, I'm realizing this is a rather, what's the word, abstract thought. Bear with me here. So let me use a specific example to put to explain this, which is actually very relevant to today. So now I have this sum of possibilities AI, and I'm looking at the intersection of how those possibilities overlaps with the state B. So let me give some very specific example. Suppose you have a population, people, and you know that 0.1% of those people have a disease, call it COVID. And then that 99.9% of the population does not have that disease. And suppose you have a test that returns a positive result if the person has the disease. Let's say you've done a lot of experiments and you know to a high degree of certainty that if the person has the disease and they take the test, there's a 98% chance that you will get a positive result if they have the disease. But even if they have the disease, the test is faulty, and maybe there's a 2% chance that you'll get a negative result even if the person has the disease. So this is what we call a false negative rate. Okay. Now, conversely, let's say we know the test, again, it's not perfect. And let's say the person doesn't have the disease, but 3% of the time, this test will say there's a positive result, even though the person doesn't have the disease. So as you probably heard in the context of COVID, there's the difference between the rapid antigen tests and the PCR tests. And you hear this language discussed in the media that, oh, the rapid antigen tests have a higher false positive rate than the PCR tests. And so that's what this is here. You don't have the disease, but the test comes back positive. That would be a false positive rate. So personally, this happened to me, or not me, but my brother. He went on a trip. He came home, he took a rapid test. It came back as positive. And this was like earlier in the days of the pandemic, like it was right after people started allowed to travel again in the United States. And so he got really worried because he'd already gone to see a few people. And then I remembered my partner, she had read these tests, they're known to have like something like a 25% false positive rate. So then he felt a little relief. He went and got one of the PCR tests and it came back negative. So again, this is a case of a false positive rate. And so the question to ask, so this is this conditional probability, trying to put a real world example onto this. If you take the test and you get a positive result, what is the probability you actually have the disease? Okay, so again, you have the disease, what's the probability of a positive result? Or we want to flip that around and say, given a positive test result, what's the probability you have the disease? If I apply this formula, so here I have the probability I have the disease given a positive test result. So here, the numerator, we have a probability of the disease, probability of a positive test given the disease times the probability of having the disease. So again, in the population, only 0.1% have the disease, so that's 0.001. And then if you have the disease and you get a positive rate, there's a 98% chance the test will record that. But then I have to normalize it by the two possibilities, which are that I have the disease and I get a positive result, or I don't have the disease and I get a positive result. And then when you take this probability, you see, you'd think there's a high probability a positive test result will mean you have the disease, but in fact, it's only 3.2% in this particular example. So you can see this is why it's very important to have to basically understand probability, but also to have very accurate tests. So here I leave it as an exercise to you. What would the false positive rate on the test have to be such that if you got a positive result, there was a 50% chance or greater that you actually have the disease? So again, the only number you have to fiddle with here is the false positive rate. What's the probability? What's the false positive rate you would have to improve this test by such that the probability you have the disease given a positive test result is actually 50% or higher? Okay, so let me jump to the next. So here is just a refresher of some probability distribution functions. Okay, there's a bunch of words. You don't have to understand what even half of them mean, but you've probably all heard of Gaussian or normal distributions because these come up all the time in physics. And basically what these distribution functions are is just like an integral is the limit of the Riemannian sum of an area. What we want to do is imagine that we have the ability to take a very small change in some input parameter x, say, and understand the probability of something happening based on some very infinitesimally small input parameter x. And so if we imagine this limit, then that's how we generate these distribution functions. So this is just, Gaussian, you know what a Gaussian looks like. I'll plot it probably on the next slide. And just as a reminder, so Gaussians are very nice functions in physics. They come up all the time. We often try to manipulate a problem so it looks like Gaussians if possible, because they're very easy to integrate and differentiate. And again, the statement from before that the sum of all probabilities has to be 1, if you take the limit where somehow you're able to get a continuously differentiable, like a smaller and smaller ability to change the possibilities I, that just turns into an integral. And so this is the same statement. If you sum over all the possibilities of some distribution, from minus infinity to plus infinity in this case, then you have to get 1. So something must happen. And then often you'll see this language E of x is saying, what is the expectation of some value x given my distribution? And here you can show that the expectation of x for Gaussian is given by, here mu is the mean value and sigma is the width. And then you can show, of course, the variance is sigma squared. And the reason we like Gaussians is because here's something that's going to come up a few times in the lecture, is we have this central limit theorem. Again, I don't have time to really go into all of this, but the central limit theorem is basically a statement that if you do a whole bunch of measurements and you increase the number of measurements and they're all uncorrelated and random, that no matter what the underlying distribution is, under fairly general conditions, as you increase the number of samples towards infinity, any underlying distribution will give you a Gaussian distribution of the mean value. And so this is very important. This underlies a lot of how we understand how to analyze the world. This is a central limit theorem. Okay, and then I'll just leave it as an exercise because I'm talking too much to prove both the expectation value and the variance. Just a reminder of some algebra or calculus. If you start off with this expectation value, then of course here you have this integral here. You're free to make a change of variables, x to y, and then once you do that change of variables, you haven't done anything special other than swap in limits on x for y, and then also change this x into y plus mu, and then just things to, refreshers, because if you haven't thought of them for a while, here I have a function that's even in y. If I change y to minus y, I get back the same value. And this is an odd function of y. So if you're integrating over the domain minus infinity to infinity of an odd function times an even function, you get 0. And so you get left back with this piece disappears and you're just left with the mean value mu, and then you'll recognize this Gaussian integral. This is just the normalized Gaussian integral. So it integrates to 1 and I get back the mean. And as an exercise, I forgot to write it down. You should go and confirm that, in fact, that's the variance you get, which is just a second order moment. So this is the first order moment. The variance is a second order moment. Okay, so now some pictures. Another special distribution function comes up all the time is the chi-squared distribution function. And I'm just writing this down for you because we're going to talk about chi-squared least squares minimization. And what is the chi-square distribution function? Well, it's given by this formula. Nothing deep in writing down the formula. And here, this is the gamma function, which if you evaluate the gamma function at positive integers, then this is just related to the factorial function. And so I leave it as an exercise for you to show that the expectation value of the chi-square distribution function is n. Well, this parameter n here is called the degrees of freedom. And then the variance is given by 2n. And so you'll often recall hearing when we talk about data analysis, people will often say, oh, the chi-squared per degree of freedom is about 1. So I know I have a good fit. And so that's kind of what we want to talk about in these lectures, is understanding where that comes from. But the first one to notice is that the expectation value of the chi-squared distribution function is n. So here I've plotted this chi-squared distribution for various values of n. And you can see that the expectation is close to the peak of the function. And again, remember though, if I'm looking for the expectation, I have to integrate not only the distribution function, but I have to multiply it by the first moment. Right, so I'm multiplying it by x, or in this case, by n. And so then if the expectation value of the distribution function for n degrees of freedom is n, then I think if the highest probability of this function is just to return the number of degrees of freedom. And so that's why we come up with this rule of thumb that a good fit is described by a chi-squared per degree of freedom of about 1. Okay. And then what are we really doing with these different tests? Well, what we want to, again, we want to try to infer the underlying theory based on some observations. Or another way to say that is we want to infer the probability of a given hypothesis. Here, H is some hypothesis, meaning it's going to be sunny tomorrow, or it's going to be cloudy tomorrow, or some other sort of question. We want to infer the probability of the hypothesis given some underlying data we have, which maybe there's some parameter X, or this is some input parameter. And so then what we want to do is come up with these understandings of how confident are we in an answer. And so this picture here is just to kind of give you a visualization of, as a user, you get to pick some threshold. Where do I want to make the choice to decide whether it's H0 or it's not H0? And so here I have some different distribution I'm calling H1. So these H0 and H1 you can think of as some underlying theory you have to predict a given outcome. And then this is a way to measure how confident you are that theory is correct. And so the significance level, as this is just a definition, is this parameter often called alpha. I'm going to integrate from this cut value up to infinity against the probability distribution function of x, assuming the hypothesis H0. And so here, if you find that X is less than some cut value, and again, this is something I get to pick, the user gets to pick, then you will not reject H naught as a hypothesis with some probability 1 minus alpha. What this means is, even if H naught is true, there's some chance you're going to reject H naught as a hypothesis. Like maybe you happen to measure an outlier, and so you end up with some value of X cut up here, and so you reject H naught as being true. And the only way to really infer this is to do the experiment over and over and over again to see what the distribution of results is based on your hypothesis. Or conversely, another way we can think about that is, suppose H1 is the true description of what's going on. You still have a chance to accept H0 is the truth, even if H1 is true. And this is given by a measure of integrating from minus infinity up to the cut from some H1 function, probability function for H1. So now, again, to try to give you a specific example, maybe this is still a little too abstract. We'll see. Suppose you have a detector and it detects particles flying through it because they are charged and they ionize the material. And maybe your hypothesis H0 is that you've detected an electron, and hypothesis H1 is you've detected a pion. And so you might think, oh, well, those two particles are very different. They have very different masses. So it'd be easy to figure out what's going on. Well, it's easy, yes, if you had some ability afterwards to take that particle and then stick it in a spectrometer and actually measure the charge to mass ratio. Or maybe you could observe how that particle decays or doesn't, but maybe you don't. Maybe your detector can only detect a charged particle flying through it, and you can't actually infer information about its mass. In this particular example, let's say the electrons are the signal. You want to know how many electrons have come through your detector. And pions are the background. So pions can leave a positive signal, but you don't want them because they're not what you're looking for. So that's what we call the background. So then let's define what we call selection efficiency. And so here we can say the efficiency to detect whether I've observed an electron is going to be given by the integral from minus infinity up to this X cut, based on the distribution function, the probability of finding X if it's an electron. And so you'll notice, compared to before, I integrated from X cut to infinity, which is alpha, but then remember the integral from minus infinity to infinity has to be 1 because something has to happen. And so here I have the opposite, minus infinity to the cut. And so here I just get 1 minus alpha by definition. And then the efficiency of detecting pions will be the same sort of integral, but here I'll call that beta because this is my background. And again, you know, the experimentalist or the scientist is going to choose a value of X cut, because what you want to do is you want to minimize the pollution of background into your information. And so you have this trade-off. If you increased X cut to infinity, then your efficiency of detecting electrons would go exactly to 1. But your efficiency of your interpretation of the particles coming out would now be polluted by some pions, because you would also be accepting some number of pions into your background, or some of your pions would sometimes a pion would go through your detector and you would call it an electron. So this would be a pollution of your system. Okay. I'm going to, I think, skip the next slide, given I've just looked at the time. So let me just leave you with this for the rest of the day. So this is what we're going to come back to, and we're going to get our hands dirty. So oftentimes, what you really want to do is, you don't necessarily want to compare one hypothesis to another, but what we do often in science is we say, I just want to test a single hypothesis. I don't want to test hypothesis 0 versus hypothesis 1, but I just want to test a single hypothesis. And this is what we often call the goodness of fit. So if I have a hypothesis and I have the data, how confident am I in that hypothesis? Well, there's several questions to ask. One, how confident am I in that hypothesis, that particular theoretical model being true given my data? And the second question is, I come up with some model and it's going to depend on some parameters. How well can I infer information about those parameters given the data in my model? And so this leads us to the often called the chi-squared test, the Pearson's chi-squared test, which is also known as a method of least squares. And these are all what you call maximum likelihood tests. So this is coming back into probability again. You're trying to maximize the probability of some function. That's why it's called a maximum likelihood test. Here, this is not machine learning, but it's maximum likelihood. And so this central limit theorem is going to come back in. How does this come in? So let's say you're doing an experiment many times, in this case, capital N. And so you have some set of measurements. And if each of these measurements is, you can think of it as a Gaussian random variable. So there's some random fluctuations. And you do the measurement, the probability of all the measurements based on the model is going to be given by what's called a joint probability distribution, which is just, you'll notice, a product of a bunch of Gaussians. And so you'll recognize this argument of this exponential is, if you studied statistical analysis, this is the chi-squared function, right? And so the way we get at chi-squared is we ask a maximum likelihood, which means we're going to end up taking a logarithm of this function. And then what we want to do in order to maximize the probability, because the minus sign in here, what that means we want to do is we want to minimize this function in here. So again, least squares, we want to minimize the chi-squared. And really what we do is we have some data y with some uncertainties on those measured data values. And then we assume that there's some true value of y that we're going to try to guess through it. I shouldn't say guess, we're going to try to infer that true value of y. And typically what we do is we say, I have a model here. Lambda is a function. It's a model of what the data should be as a function of some input parameters, x, like how far along, in x are you, how fast are you going, based on some parameters theta. And really the goal is to understand how well can we infer the value of some unknown parameters theta given the model and given the data. And once we do that, how confident can we be that this model is a good description of the data? So it's already been an hour, well, I guess minus the 7 minutes of goofing around at the beginning time. So it's already been sort of, I don't know, close to an hour. So what I wanted to do is leave you with this, and so you can go read about this stuff on Wikipedia or in your favorite book. And then on Thursday, we're going to come back and actually put all this stuff into practice. And again, it's just going to be a survey of what's going on. And I want to show you the difference between doing frequentist analysis versus Bayesian analysis. And I'll give you, problems where you have, so this is a very simple case when the data between different measurements I is uncorrelated. So Y1 and Y2, those measurements have no correlation with each other. But most often when you do experiments, you actually have correlation between these measurements. And how do you deal with correlation? You can have models where you have, you can, you have a linear dependence on the parameters theta. I'll define all of this with actual formula, or you can have nonlinear dependence on the parameters, or you can have situations where you have some parameters are linear and some are nonlinear. And how do we optimize our ability to infer the parameters theta? Because everything we can prove about least squares minimization can only be proved in this, nice theoretical limit that we have this central limit theorem taking over, so that everything is described by a Gaussian, and also when the model function only depends linearly on the parameters. And what I mean by linear, like maybe y equals x, or equals like a plus what? Okay, come on, the line for a slope y equals mx plus b. So in that case, m the intercept and b the slope, the function is linear on those. Whereas if it equaled, okay, I won't try to say it. I'll just show you an example next time of everything I'm meaning. So here today, I just wanted to get these ideas into your head so you could go think about them. And then on Thursday, we're going to put everything into like a hands-on sort of fitting exercises where we have correlated data, uncorrelated data. We'll fit the data that Andrew used in his talk last week on the neutron proton scattering amplitude or cross section. Okay, so that's what I have today. Do we have any questions? Was this too abstract? Maybe it's probably too abstract, but
If it's too abstract, I'm sure there's even more questions.
I'm not seeing anything myself, so I assume that means people are quiet, but it could also equally mean that I just don't know how to see what's going on.
No, people are quiet. I was gonna say that we could have maybe given them a little bit of time to ask questions about some of the first examples, but
Sure.
but now we have all the time in the world. How are people doing? Are people awake? Let's start with that. We'll ask the questions first. We got Amar say he's awake. That's good. Appreciate it, buddy.
It's good to be awake.
Yeah. You do have a soothing voice, so.
Yeah, it is a problem. I was putting myself to sleep there. This is a common problem. I'm a very good sleeper.
Yeah. Yeah, we have a few people saying they're awake. That's good. That's good. Those of you that are awake, do you have any questions? Is everything super clear, or do you just need more time to digest it before you can ask the questions?
And as you're thinking about answering that question, I will also tell you the way I learn best is always by example. And so this kind of abstract thing is always difficult for me until I actually get a real world example and start playing around with it. So
Yeah.
hopefully, well, if you have a similar feeling, hopefully Thursday will make things a little better. And I'll come up with, I'll also distribute some Python code and some data files. And
Good. It's great. Yeah, this example always kind of blows my mind.
yes, I remember it came into my mind because that story I had with my brother where he had this false rapid test. And I was like trying to remember, you know,
Yeah. Do you know how effective the test that he was taking is?
the one, so I don't know exactly, but I do recall, I believe Erin, she read it was something like a 25% or 50% false positive rate. But I don't know if that's really what was going on, or really it was more the false positive rate was, I don't know, maybe 2%. And so then the probability of a false positive, this number here was only half.
Yeah. Got it. So the probability of you being sick given a
What's the probability
positive
you're
test.
actually sick given a positive test? I think this is a perfect example of how complex probability can be and how difficult it can be to assess the truth of what's going on.
But
Because this, you get a positive result, you'd be like, oh my God, that's super scary. And then like, if you do a little, most people can't do this math, right? Because most people aren't trained to think about this. So this way, if you learn, you can walk your family through the math and they're going to roll their eyes at you.
yeah, you're assuming that your family would allow you to even walk them through the math.
No, they'd roll their eyes. They wouldn't walk. Their like brain would go off somewhere else.
Yeah.
You just have to drag them to the answer. They
Yeah.
still won't believe you. Do you guys have any
Well,
other questions? It doesn't have to be about the lecture. You can just,
it seems like people are kind of shy today.
that's okay.
How is, maybe we can ask more questions of them. How's everybody doing? How's the
Yeah,
weather in your part of the world?
how's the heat where you guys are?
Yeah.
The weather for me looks something like my background today. It's cool, overcast. Looking at the question.
Somebody asked, if I remember correctly, we used to calculate accuracy and precision. Does it relate to today's lecture?
Very much it relates to today's lecture. So let me see if I can scroll to a formula. So this will not have the full answer to your question, but I'll just try to say some words. I will say some words that I hope will infer some answer to your question. So there's precision of measurement, and there's also precision of the parameters theta. And so your question can mean both. What we ultimately care about is both how accurately we can estimate the parameters theta and how precise. And if you have a model like we have written on the slide here, then all you have to do is increase the number of measurements you make of a given system, and then this parameter sigma will get smaller and smaller, which means it's becoming a more and more precise measurement. And what you can show is, in fact, we'll show on Thursday, as you make sigma more and more precise, that directly gives you more and more precision on the parameters theta you extract. So that's perfect. It's a perfect theoretical way we can think about trying to understand information about the parameters theta based on the precision of the measurement. And of course, there's going to be a but there, which is that in almost any experiment you do ever, there's going to be what we call systematic uncertainties. And a systematic uncertainty is not going to look like this nice, simple Gaussian distribution function. And the systematic uncertainties are going to cause problems with accuracy. And yeah, you've probably seen this cartoon, I'll draw up again. Like, we can't be only accurate and we can't only be precise. We have to be both accurate and precise to infer what's really going on. And so we'll talk about that definitely more on Thursday. No, so someone's asking if they have to submit weekly reports to nuclear mentoring program if they're only registered for the data analysis. I'd say, I don't think so, but I don't have the ultimate say. I assume that's correct. Is that?
You do have the ultimate say about that.
Do I? Okay.
Yeah, you can set your own standards for the people that are only interested in working with you on data analysis and not on the nuclear mentoring part.
So the answer to that is no, you do not. I encourage you to listen to if you have any interest in physics, I encourage you to listen to all the nuclear mentoring projects, but you don't have to submit a report for those. Okay, very good.
And for the record, if you've missed any of the lectures, they're all recorded, posted on YouTube. I keep sending the recordings links in the Slack chat. So
Aha, I see there's some chat questions too.
yeah.
It's a good cloudy day. And also, yes, so the question, in case people aren't reading, is I recognize a lot of these from AP statistics class I had, but with very different notation and symbols. Are the ideas still comparable? Just the examples contain more physics-centric jargon notation. And unfortunately, the answer is more or less yes. Physicists often use the exact same math, but will use very different symbols and jargon. And that's just an unfortunate reality of life. So hopefully you'll recognize the math and then be able to tease your way through the jargon, if that makes sense. Like once you get comfortable enough with the equations, then it doesn't matter if I call this y or x, right? It's just in physics, we almost always call measured data y, and then parameters, which are input parameters, we call x. That's just very common. Here I've actually, why did I call the expectation of the mean value lambda? I have no idea. Usually I call it a different symbol, but this time I called it lambda. I will be self-consistent, between today and Thursday when we talk about these things in more detail. At least I will be self-consistent, but I won't necessarily be consistent with myself at other times in my life.
Yeah, I was gonna say that's a tall order.
Yeah.
Yeah, I think once you become fluid with these concepts and you learn, that across different fields and even across different papers in a subfield, people will use different notation. You just get quicker at understanding the math within the context and just adopting in your head the jargon and notation in that context. Sometimes it is a source of endless frustration, but most of the times you get used to it.
Right. And even today, I still will get confused because somebody will use a symbol that I mentally associate with something else. And so it takes a while, like, you think the person who's talking thinks they mean one thing and you're listening and you think they mean another thing. And it takes a little back and forth to readjust your brain. Like sigma always means uncertainty, right? But then someone else may use a different variable for uncertainty and I'll just get confused, like, wait, what? No, sigma's the uncertainty. Like but someone might use sigma for the mean, and then that will break your head. But okay. Someone asked a question, Abhinav asked, for the COVID question.
So actually, Abhinav can ask the question live because they have the ability to share their camera and turn on their mic if they want to.
If you're welcome and comfortable with that, please feel free. If not, you can just stay quiet for.
Hello.
There we go. Okay, hello.
Hello. Yeah, I just wanted to ask that in that exercise question, is the false negative rate the same as 0.02?
No. So here you see, this is this conditional probability. So, or maybe the answer to your question is yes, I was just hearing it wrong. The false negative rate here, what I mean is if you have the disease, but the test comes back negative, that happens at 2% for this hypothetical test. And notice the order here is different. Like this is a plus on the left and disease on the right, whereas down in this equation down here, we have disease on the left and plus on the right. So I'm flipping the condition, right? So if I get a positive test result, what is the probability I have the disease? And I guess, let's see if I can edit this live.
Right, I got that. So we need to find the false positive rate, right? But the false negative rate still remains the same. I just wanted to confirm that.
So specifically what I want is I want to change this, here by false positive, what I mean is yes, the false negative rate stays the same. I think that's your question.
Right,
You're
right.
changing
Yeah.
this and not this. Yes. So,
Okay, thanks.
because again, the test, like these numbers are made up. They don't necessarily have anything to do with each other other than the fact that it's the same test, right? But the test could have some impurities so that it's detecting some other protein in your body, which is why even though you don't have the disease, it still registers as a positive. So the test may, like you have two chemical elements that are very similar. Maybe they just differ. They have the same proton number, but they have a different neutron number. So they have a different isotope. Now that's too specific for this kind of a test because these tests are detecting proteins as opposed to individual atoms. But, maybe the test is picking up on some very similar protein to the one that's giving you the disease, but it's not the right protein, but it still will say positive. And so yes, this is the number we want to fiddle with such that this is at least 50%. So presumably
Thanks.
you're comfortable enough with this, you can go off and you can either invert the formula and solve for it exactly, or you can fiddle around with the numbers and deduce the answer.
Cool. Are there any other questions, comments? If not, why don't we give Andre a warm virtual thanks for taking the time to talk to us all the way from sunny Bay Area.
Yeah, thank you everybody for showing up. And hopefully Thursday will feel more real. And unfortunately, I won't be able to join you guys on the social today because I'm participating in a workshop this week. So I'll be taking questions offline and on Slack. So, I'll be in a workshop, so I'll still have my laptop, so maybe I can answer some things on Slack. But otherwise, I'll see you guys Thursday.
Yeah, just remember, if you have any questions, it would be great to put them on the Slack chat. And there's a social hour coming in. Is it 2 hours from now?
Andrew might know, but he's muted.
I've lost track of time. Yeah, 2
It's
hours.
at 2 p.m. So yeah, hour 45.
All right. All right. Well, take everybody, and we'll see you guys later. And Andre will be back on Thursday.